So, just to recap, for us to try to do some calculus on the polar coordinates, we changed it into parametric equations because we know, I was going to say we know all about parametric equations, but we know quite a bit about parametric equations. We know the derivative of parametric equations. We know how to find the slope of a parametric plot. We know how to graph it. So uh, this will allow us to go from polar to parametric to be able to find things like the tangent line, equation of the tangent line. And for that, you need the derivative dy dx. And here's the derivative dy dx for us. Okay. So the next thing to do is find areas. Now, for parametric equation, we found like the area under the curve if we're looking at it from top down to x and to y. But when we're doing polar coordinates, and you saw the polar coordinate graphing paper, how it's just kind of made out of circles, it would probably make sense to find the area of sectors of circles or sectors of things that might look like circles. So in that sense, what we want to do is we want to remind ourselves of the area of a sector. And do you remember what the area of a sector is? So let's say if we have an angle theta and a radius, and let's say this is a piece of a big circle. Anybody know what that area is? Yeah. Theta over 2 times r squared. Okay. So it's 1.5 r squared theta. That's the area of sector. So just like with in Calc 2, we found the area under the curve and we looked at areas of rectangles. Here, we're going to find the area that's spanned by a polar coordinate graph, and then we're going to use the sector instead of a rectangle because that makes a lot more sense. So if we had a graph, a polar coordinate graph, and let's say we want to find this area here. Now let's blow this up a little bit. How do you blow that up? So what we're going to do is we're going to find areas of little sectors. Little sectors. And so I can't draw straight lines. Yeah, something like that. Let's say this is an actual area of a little subsector. And so this has a radial distance. Well, describe the radial distance for me. Yeah. It's distance from the center to the point or center to the function, and that is usually referred to as like f of theta. And we're going to imagine that we're going to partition this into little bits and pieces of sectors, right? And so at some angle theta sub I that's like involved right here, we put that into the function and we're going to get the radial distance. So that's going to describe the radius. Now, theta sub I and theta sub I minus 1 might have two different radial distances, right? So if we blow that up, let's blow that up. So your radial distances might be different, right? But we're going to take so many of these cuts anyways, and we're going to let the partitions go off to infinity that it's not going to matter. So that's what the Riemann sum is about. Okay, so that's radial distance. What's theta going to be? What is this? What is this angle? No, well, we don't know. It depends on how many cuts we make and stuff like that. Well, what am I going at here? What should this be? It's the change. It's how it's changing according to one angle to the other. Delta theta. So 1/2 r squared delta theta. We add them up, a whole bunch of them, and it becomes an integral. So I should copy the rest of that. So the area within a polar coordinate graph, r is equal to f of theta, whatever that might be, from theta going from a to b, for theta going from a to b is going to be the 1/2, and then the r squared, which is f of theta squared, and then the theta, the angle, is going to be delta theta, which will, in an integral, become d theta from the beginning to the end. Okay? So let's do an example. One of the graphs, I think group 3, 2 or 3, and I was encouraging people to, if they had already finished their activity, to graph the other graphs just to get an idea of what they might look like. Does it sign? Look at the cosine. Cosine 3 theta has 3 leaves. Let's change it into sine. Oh, it also has 3 leaves. But you see where it starts and how it looks different, right? What if there's 4 leaves? 8. Ooh, 8. What if it was cosine? Is it also 8? What if it was 5 theta? 5 leaves. You get the pattern? Okay. So there's patterns to these things to try to remember and try. It's not, I don't know if it's worth memorizing. You guys have a lot of other things to try to remember in this class. But it's a neat little pattern between the sine and the cosine. The cosine of something times theta gives you some sort of leaves to it, and then it depends on whether that coefficient is odd or even. It's either n leaves or 2n leaves, depending on what they are. Put a weird number here. Pi. Whoa. So actually, if we just go to 2 pi, or let's go to pi over 3, pi over 3, pi. So it looks like it almost wraps up this whole leaf, right? But then when it starts growing, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. And so what happens is it keeps going, but it can never repeat itself because it doesn't, it's not, the period is not the same. It doesn't fit into a whole number. So any irrational number will give you this sort of setup. So if I go to like 100 pi or something, well, maybe that's a little too much. Yeah, now it's frozen. Uh, 7 pi. Whew. All right. What did I say? 100 pi. Well, just 100. Let's just go 100. So it repeats itself. And if we change this into another irrational number, what's another irrational number? E. Kind of get the same thing, right? And if you keep doing this, it looks like it'll fill up the whole circle. Anyways, that's what were we doing? Just 3. We just want 3 pi. Can this be done at pi? Yeah, looks like it's done at pi. It looks like it'll repeat itself, right? That's probably what it means. So I think I wanted to do sine. We can do cosine. I'll do sine. So what are we talking about in our lecture? Areas. Oh, areas. Let's find areas. Let's say we wanted to find the area within one leaf of this. So let's draw this, or better yet, let's just copy this. So let's say we wanted to find r is equal to sine 3 theta, one leaf. I don't know if they call it leaf or petal, but let's just say we want to know that. What is going to be our issue when we're trying to solve for this? Yeah. Finding the limits, right? We want to know when to start and when to stop. So I think that'll be a little bit of an issue. So you have to know what theta value will give you the starting point and what theta value will give you the ending point. Because if you go theta goes all the way to 2 pi, then you're going to get all these things, and some of them are negative also. So that's even going to get some weird other things that you might not want. So what is it? Yeah. If you use bounds that are bigger, then you're counting more area, or like I said, if the area becomes negative, you're counting the area and then you're subtracting out areas. You think it's between 0 and pi over 2? but if we go 0 pi over 2, we would get that area in the first leaf, and then it goes negative, right? Because this goes negative, so in fact, if you draw this, you can kind of get a feel for what are you looking for. Not quite the period. 0 to 0, right? You're looking for the radial distance that's going to start you off at 0 and then get you back to 0. And if you look at the graph of this, you can kind of see it starts at 0 when x is equal to 0, but it also ends over here. Desmos gave us the answer right here. Pi over 3, right? So if I take this to pi over 3, I get that one leaf that I want. So when you're finding areas here, the most difficult part will probably be try to figure out the boundaries. Okay? So we are looking at this, and one way to do this analytically is that we know that it's equal to 0. R equals 0. It's the starting point of the leaf that we want, and then at the ending point of the leaf. And so what we could do is we can set your function equal to 0 and then solve for theta. Now, I know you guys really enjoyed trigonometry and solving for these things. So we get to use it now. Yay. Okay, so the sine function, sine of an angle is equal to 0 when 3 theta is equal to 0. It's also equal to 0. What's the first time? The sign goes up, and when does it come back down? At pi. And then 3 or 2 pi and n pi and stuff like that. So let's not get into that. Let's just take a look at these two scenarios where we get theta is equal to 0 and theta is equal to pi over 3. And then with Desmos, you can double check to make sure that this is actually what's happening in your graph. So now you have limits. After that, you're done. Well, pretty much. So then the area is going to be 1/2 integral from 0 to pi over 3 of sine squared 3 theta. This is the r squared. And then your angle delta theta will become d theta. And now this is an integral. Okay? So if you want to brush up, if you're tutoring, by the way, I encourage you to tutor from algebra to Calc 2. And if you're tutoring Calc 2, you would remind your students that you would need to do some half-angle formulas to solve for this by hand. But since you're Calc 3, you can just plug it into Wolfram Alpha or Symbolab or whatever. Okay. So if we plug that into Desmos, which apparently you can, we'll get our answer. Int. I wonder if I need a space there. There he goes. Yes. Oh, thank you. Okay. So the area of this whole box, again, so using your eye to estimate the answer. Did I get that answer correct? You know, that string activity that we did? The whole area of the square from 1 to 1, the 1 to 1 square is 1, right? This is clearly, if you got a number bigger than 1, you did something wrong, right? And so it looks like it's less than 1/2. It looks like it's maybe a quarter. So does that area make sense? Looks close enough, right? Find that area. I changed this equal sign into a less than sign. You can change it into a greater than sign or less than sign. Less than or equal to. Then it's not double lined. I mean, it's not dotted line. Anyways, that's our answer. Questions? Yes. I think first of all, the picture would be good, getting some idea of what the graph looks like, and then after that, if you can do it on a graph and guess and check, that would be helpful. Or better yet, if you could do it analytically, like in this case, we know that the starting and ending points here are when r is equal to 0. And so we took it from here, r is equal to 0, and then we set r equal to 0 and solve for theta analytically. It could be. In fact, let's do another example where it might not be that easy. Now I have to make one up. It's okay. So this is one of those other common examples. Let's see. Oh, you guys saw one of your graphs? Was not quite a cardioid. It is still considered a cardioid, except that little cusp doesn't go all the way down to 0, right? Doesn't go all the way down to 0. And let's see. Should I make this 1? Let's get this a little bit bigger. Circle radius 4. Oh, what happened? All right, let's say we wanted to find this little area down here. So we got a circle of radius 4, and then we got this cardioid looking thing. Minus, plus, minus. Okay. Again, the hardest part is probably going to be the limits. So let's figure out what these limits are. And we would be able to figure that out by how? They intersect, right? So whenever graphs intersect, usually that's the key, is we set them equally, set something equal to each other, right? And so we're going to set 4 equal to this. So analytically, that's what we can start. Set them equal. So we have 4 is equal to 3 minus 2 sine theta. And then just solve for that. Well, just solve for that as if it was easy. So this is 1 divided by negative 2. So it's negative 1/2 sine theta. So sine is equal to 1/2 at like pi over 3, pi over 6. Pi over 6, but it's negative, right? 7 pi over 6 and 11 pi over 6. Wow, you guys did that too fast. Slow it down for me a little bit. I'm sorry, this is an equal sign. So we want to remember your trig. Sine theta is equal to 1/2 when theta is equal to pi over 6. So that's the starting point. And if you don't know that, try to recreate the table. You guys know how to recreate the table really quick? Why am I doing Yeah, 0, 1, 2, 3. Sine's first, cosine second. Square root of 0 over 2, square root of 1 over 2, square root of 3, 2 over 2, square root of 3 over 2, square root of 4 over 2. That's how I remember my signs. And 0, this is 1/2, root 2 over 2, or 3 over 2, and this is 2 over 2, which is 1. Right, so I just remember root something over 2. That's my sine. My cosine is backwards. You're welcome. All right, so now we know that sine of pi over 6 is equal to 1/2, and then the other parts of trig that you probably should know, all students take calculus. The sine is positive above here because that's where the y is. The sine is negative down here. And so with an angle of pi over 6, you have a couple of reference angles down here, or the reference angle is pi over 6. And so a couple of angles down there would give you these two angles that we're looking for. So each of these angles are pi over 6, but we want to figure out the angle from here to here. Okay, so pi plus pi over 6. So that's 6 pi over 6, 7 pi over 6. So 7 pi over 6 for the first one. And then this is 2 pi, which is 12 pi over 6 minus pi over 6. That gives an angle of 11 pi over 6. Okay. Now you've found your limits, plug it in, you're done. Yeah. Well, let's think about it. In the number line, if you use minus pi over 6, you're going in order, right? So you're looking at it in an integral way. What do I want to do? Okay, so if we integrate, so 1/2 integral from, what is it? All right. I guess hard to tell unless you can see. So this is 25, and then this is a small sliver of that. I can't tell. Does that look right or wrong? Oh, yeah, we're also missing something. Sorry. What are we missing? Oh, it's negative. So there's all kinds of wrong here. No, so to answer your question, um, yeah, we need the shaded area. So let's just say this is sad. No, no, no. We got computers and stuff, so why bother? So let's think about what did you say if you go from pi over 6, negative pi over 6? So if you go from negative pi over 6, you're actually starting here. I need different color. And then if you want to go from negative pi over 6 to 7 pi over 6, and 7 pi over 6 is here, you're actually looking at this area over here. And you're looking at this area. Now, this area, 4, r is equal to 4, is bigger than the other one, which is why when we put it into the calculator, we got a negative number. Okay, so what we had found here was the wrong area. Not just the wrong area, but we did it in the wrong order, so we even got a negative number. If you want that area in positive, which is not what we want. So here's our issue. Shrink. Okay. So here's our issue. Doing this gives us this area, and we even put our functions in the wrong order. So if we switched them, we would have gotten a positive area, but then it's still the wrong area that we're looking for. Okay. So instead of doing this, which is not the area, we want to actually integrate from 7 pi over 6 to 11 pi over 6. So let's put that into our calculator. And we see something that might make a little bit more sense. It's about 6 point something. What? No, because this time you have to turn your head all the way upside down. The larger area is the cardioid, 4 is the green graph, and that's shorter. So this is in the right order. We got a positive number, and we got the right limits. Say it again. Yeah. So when we're going from here around here, then we're looking at these two graphs here. Whereas down here, we're looking at this graph, the red graph. This one minus the green graph, the small graph. Yeah. I think basically it's the outer one minus. Outer, yeah, outer inner, instead of turning your head upside down and saying top and bottom. Yeah. Or what? Yeah. I think it's the same. So come on. Uh-oh. So this is what we really want. Now it wants to be done. Said, I'm tired. You're making me work too hard. And so even better if we can see this, if we actually take the limits. What's the top function? What did you say? The outer function. What's the outer function? So r, what is it? 3 minus 2 sine theta, and then less than r less than 4. That work? No. On the theta? What? Oh, this is the upper one. Sorry. 4 less than r less than 7 pi over 6 less than theta less than 11 pi over 6. No, it still didn't work. Well, anyways, I'll try to see if I can get this shaded, and it didn't work. So for areas, the hardest part will be finding the limits. But then if you draw your graphs, if you do the equation symbolically, you should be able to get it. You have a quiz on Monday. You have a quiz on Tuesday. I don't like pop quizzes. It's only a pop quiz if I forget to announce it. So I'm announcing it. All right. All right, Sean.